Hello everyone. I'm honored to be one of the speakers in this year's AKC 2021. My name is Shah and I am an alumnus of Professor Cho Namjoon's Translational Materials Innovation Group, having been there from 2018 till 2021. I have been working on sustainable plant-derived materials since I joined the group. Today, I am delighted to present to you some of my POLLEN research while in TMIG before transitioning to the work I'm currently involved in with Audra Labs, where we utilize plant extracts to generate 3D constructs. So while in TMIG, my work was largely focused on translating pollen into novel engineering materials. Pollen are hollow microcapsules encapsulating genetic information that plants require to propagate. The unique shape determines not just the method of dispersal, but also the selectivity of the pollen towards its own species. Pollen is an interesting subject matter because it is highly uniform, with low monodispersity, are selectively porous, and most importantly, with regards to global sustainability, they are abundant. In general, pollen are composed of several common layers, namely the outer pollen cement, the exine, the intine, and the genetic material that is encapsulated within. The intine is largely composed of cellulose and pectins, while the exine is composed of sporopollenin, which has been dubbed the diamond of the plant world. The toughness of the exine sporopollenin to resist harsh conditions, including acids, UV, and oxidation, are well documented, thus making the pollen overall a highly stable material, resistant to changes, interactions, and manipulation. However, with limited manipulation, there can only be limited applications. However, in TMIG, we managed to design a facile yet highly efficient process of softening the pollen. This process utilizes hydrolysis in potassium hydroxide, followed by an incubation step at 80 degrees Celsius for varied durations, again in potassium hydroxide, and finally, the washing and removal of excess water. As we can observe here, by regulating the duration of incubation, we are able to tune the stiffness of the pollen shell to suit any downstream applications. The softening of the pollen results in a viscous microgel slurry after a 12-hour incubation. The softening of the pollen is largely contributed by the de-esterification of the ester groups within the pectin network of the intine. And this was shown via immunostaining of the pectin with GIM5 and GIM7 antibodies. The resultant de-esterification leads to a more hydrophilic intine due to the increased carboxyl and hydroxyl group present. This thus allows the intine to absorb a larger amount of water, allowing it to swell and overcome the stiffness of the exine. Surprisingly, the base-treated pollen exhibits pH-dependent swelling behavior. In the presence of an acidic environment, the pollen shrinks, and this process is reversible upon subjecting the pollen to an alkaline environment. The extent of swelling and shrinking can be modulated not just by the pH of the environment, but also via the duration of incubation during the synthesis step. An exciting aspect of these new soft pollen microgels is in the fabrication of 3D sponges by simply freeze-drying the microgel slurry. Utilizing pollen microgels of different incubation duration, the sponge morphology, porosity, and mechanical property can be easily modulated. Furthermore, these sponges have a good compression recyclability. We explored using these sponges for water treatment applications. After coating the sponges with natural fatty acids in the form of stearic acid, the pollen sponges were able to selectively and efficiently absorb oils present in water, as seen here with silicon oil labeled with red dye. We also quantified the absorption of various common organic pollutants. While current oil-absorbing materials are made of synthetic polymers and have low recyclability, pollen sponges provide a green and sustainable alternative to the future of water treatment. So moving forward, I joined Audra Labs in August this year, and it has been a whole different ballgame working in a startup. So I would like to first introduce you to Audra Labs. In a world where the human population is projected to increase while arable land for food decreases, Audra Labs has a vision of providing food sustenance to the world's population. And we are doing this by innovating and developing nutritious and sustainable meat analogs that will positively displace animal agriculture, which takes up vast amounts of lands and are highly unsustainable. So one of the early challenges that Audra Labs seek to solve is capturing the texture of meat. Texture and visual appearance are critical in obtaining consumer acceptance. Currently, most alternative meat in the market utilize high moisture extrusion method to churn out 3D meat constructs. Besides it being an energy-intensive process, the resultant products do not accurately resemble meat cuts and are therefore limited to ground derivatives. As such, at the moment, there is still a lack of meat analogs with the look and texture of real meat. So Audra Labs has been working to solve this problem. Here are some examples of products that we can churn out using our fiber assembling technology. We are able to make constructs with meat-like fibrous textures and also solid fats. And as a result, our products are visually indistinguishable from real meat. And this will definitely help shift the consumer's acceptance to alternative meat. We optimize our process using many permutations of plant-derived polycationic and polyanionic polymers to stimulate a complexation process to occur at the outlet interface. The fibers that result can be effectively spun and assembled to form meat-like 3D constructs. As we can see from this video, the resultant product even peels like how a meat peels. Furthermore, our process is less energy intensive and is scalable at a comparatively low cost. And I'm sure some of you may be thinking, but surprise, this here is not real meat, but our composite product with layered solid fats between layers of protein-rich fibers. The red coloring is derived from blackcurrant. This is an example of what Audra Labs can achieve, and we hope to continue to churn out more varieties of realistic meat cuts in the near future. I would like to end my session by thanking all members of TMIG, especially to my supervisors, Professor Cho Namjoon, Professor Song Juha, and Professor Jeffrey Kulen, MSc and IGP in NTU, and also the team at Audra Labs, as well as staff from Singapore Institute of Food and Biotech Innovations for certain aspects of the work here. You may check out audralabs.com and maybe we can find some opportunities to collaborate in the near future. And with that, I wish you a fruitful conference this year. Thank you so much.